Good afternoon, I'm Tran. These are my teammates Aloma and Agudelo. For Team 15, we're presenting a speed reducing gearbox for a winch. Some applications for our gearbox can include electrical winch, elevator pulleys, and conveyor belts at airport electric systems. These are design parameters for our gearbox that we have to fulfill. Our gear ratios must be a total of 7.5. The shafts of input and output must be aligned, and also rotating in opposite directions. The gearbox must also be easily assembled. The parts must be commercially available, easy to install, compact, lightweight, portable, and cost-effective. A winch consists of three main components: a motor, a gearbox, and a cable spool. Commercial electrical winches can be rated around 12,000 pounds, but these prices can exceed $1,500. The power they transmit can vary between 6 to 10 horsepower, and gear ratios can vary between 150 to 300. We have here is our conceptual designs for our gearboxes, which includes penetrating gear trains, level gear trains, and compact reverted gear trains. These are some of the pros and cons for each systems. And for our system, we chose a compact reverted gear train because of the pro of having our ease of alignment of our input and output shafts. Our system is exactly a three-stage compact reverted gear train. Again, for the ease of alignment of our input and output shafts, and it's also with three-stage, we can easily have our input and output shafts rotating in opposite directions. Also, the other designs were not optimal to achieve our gear ratios of 7.5.
My name is Andres, and I'll be talking about the structural design of our gearbox. Like my colleague mentioned previously, our gear ratio was 7.5 to 1. In the first stage, we had a 2.5 to 1, a 3 to 1, and a 1 to 1. The product of these gear ratios does yield 7.5. The trickiest thing about this design, though, was getting the input and output shafts to align. So not only did we need to select gears that could withstand our torques, but we had to select gears based on their diameters so that we could, at the end of the day, have these aligned. So what gears did we select? We turned to the Bosch gear catalog. We use spur gears as opposed to helical because they can handle higher torques, all with a 14.5 pressure angle. The gears in the first stage are all made out of iron. In the second stage, one of them is made out of steel and the other is made out of iron. And in the third stage, all steel. So how do we know if these gears fail or not? Well, we applied the AGMA bending stress and contact stress criteria. The allowable strength of these gears are here as follows in KSI. As you can see, the stress that they would be under in the gearbox is a lot lower than the allowable strength, so the gears in turn do not fail. Same thing goes for contact stress. The allowable stress is way higher than the stress that they would be inside the gearbox, so they do not fail. This design boasts a high factor of safety of 3.2. The shafts were custom designed. A36 steel was chosen as the material due to its high yield strength. As you can see here, the maximum shear stress the shafts would exhibit is way under the 36 KSI, so the shafts do not fail. As for bearings, we turned to the Timken catalog and found that their C10 ratings from the catalog are a lot lower than the C10 ratings that we calculated. So in turn, the bearings do not fail. I will now turn things over to my colleague John Agudelo to go over engineering drawings and animation of our system.
Hello. As you can see behind me, this is the engineering drawing of our assembly, including the case and the gears. Here you see the full case, complete with nuts and bolts, completely assembled. And here's an exploded view of that. Now, on the side, you have the side view, which shows you all the tolerances and clearances between all the gears. This is a short animation where it'll show you that our shafts rotate in opposite directions, input being clockwise and output being counter. Well, there you go. So as far as maintenance goes, if this unit was ever turned in for repair or overhaul, you'd really have to worry about a few things. For example, lubrication, which you need in order to keep the gears moving, consistent, no backlash, which produces gear wear. Shaft seals, which allow the lubricant to stay inside the casing without spilling out or anything like that. And simple cleaning just to keep it clean, you know, which affects the gearbox rating in total. Our cost estimate includes the cost of the gears, which was $575 estimated. For bearings, a total of 4, $27.96, shafts 58, and the case 223, including the nuts and bolts, for a grand total of $884.98. In conclusion, we have a compound reverted gear train with 3 stages. The gears do not fail due to the criteria. The shafts do not fail, and the bearings do not fail. All the parameters were met, and our gearbox is a success.